Hey there, this is David Wong, and in the previous video we talked about cycles of curves and how we alternate curve when we prove functions, we prove circuits, because we want to be able to verify proofs that are in a field inside the circuit of the next prover, right? A proof here inside the circuit of the next prover. And because we have these cycles of curves where the scalar field of one is the best field of the other, the scalar field of one is the best field of the other, we can efficiently compute these field operations in the next circuit. This trick is actually used in more than just verifying proofs. For example, here when you verify this proof here, you will do a bunch of points arithmetic, right? And that's why we're in a different field. You will do like p plus p, this is doubling. You will do p plus q, this is adding if p and q are different. And sometimes you will do also scalar multiplications. And all of that you can do. The problem though is that the scalar is not always given like that. Sometimes it's something you have to compute for yourself. So like a plus b times c, let's say. In this case, this field arithmetic is actually not easy to compute because you're in the field that's actually targeting the best field of your curve. So the scalar field you can't really compute. So what you can do is you can just hint it. Instead of computing it, when you write your program, you can just say s equals some hinted value. And when I say hint, I mean that the prover compute that out of circuits, not within the circuit, so that they don't constrain these operations. Some people might say that the prover computes that in their head, and then the circuit just goes on and do stuff with that value that they were just given. Hints are something I've talked in the past, but you can think of like if you want to use a random number in your circuit, that's a hint. If you want to use a private input, that's a hint. If you want to do, usually when we do division is kind of hard to constrain. So what you do is that you provide C, and then you constrain that A times C is equal to B, which is easier to do. And so you have the prover just provide that value C, and then you constrain it. So all of these are hints. So this thing, let's say that to verify a proof, we have to get this value computed out of these values, and that's a hint. This thing is not secure until we actually make sure, as the verifier, that S was computed correctly out of these values. But the verifier doesn't have access to these values. Maybe, right? Maybe this is most likely just used in the circuit once, and so it's a private value. It's part of the witness in the circuit, and maybe these don't come from the public input. Maybe they're private inputs as well. So the verifier doesn't have access to them. Well, what the verifier can do is that they can use the public inputs as a message passing primitive. Or maybe not message passing, but message authentication primitive. So I'll describe what happens. The circuit that just used that value S that was given as a hint will simply provide the value S as part of the public input, or the public output, whatever. And it will also provide the value A, B, and C that are needed to recompute the value S. Now, because the verifier needs these values to input them as public inputs to verify the proof, they will need to get them from somewhere, so the prover can give that to them. And if they are not the correct values that were used in the circuits, then the verification won't work, right? That's the public inputs. If you change the public inputs, the verification doesn't work. And so that's why I'm saying that it's kind of like message passing, or like a way to authenticate messages from the prover to the verifier. And so now that the verifier has these, then the verifier can check that indeed S equals A plus B times C, which is what I've said here previously. Now, we're talking about a verifier out of circuit, but we've been talking about proof composition previously and recursion and all of that. So the next verifier might just be a circuit, but nothing changes there. The circuit will have access, will need to implement a verifier circuit, which will need to use a public input. And so you will have to pass these as values at some point. And since, remember, the verifier circuit is implemented in a different field, which is different from our previous field, we will be able to do this computation efficiently. And so we will be able to compute this efficiently. And that's all there is to what I wanted to explain. Sometimes we do these, we use this trick. Maybe I can give you the name, the deferred values. I never know, I think there's 2F, deferred values trick. Okay, let's call it that. That's the trick.